I'm going to share screen and then go to here. And you guys should see it now. Give me a thumbs up if you got it. Okay, great. All right, how's everyone doing this morning? Aside from Professor Eager, broken arm.
What happened, Professor Eager?
Slight accident in the driveway.
I tripped and fell on a brick. Landed on my elbow. So anyway.
Hope you get better soon.
Yeah, thanks.
So, starting our lecture where we always start our lecture, the most structurally efficient lightweight designs require geometry and materials considerations. That is the theme of this course. So, okay, why isn't this thing changing? There we go. Okay, last week we started off here. Well, actually, we started off finishing up the materials module, but the first part of the beams and geometry design part of this, we started here. We talked about these two different bicycle frames. We talked about the Colinago and the Cinelli, separated by, 45 years. And we talked about how these two frames are both made of steel, but one is significantly lighter than the other. And it's that way because it took advantage of not only new materials, but also geometry. They make this frame more structurally efficient by increasing the tube diameter and decreasing the wall thickness, and by taking advantage of the, oh, hi, Steve. Steve's back. Anyway, they take advantage of the increase or decrease in stress with the radius to the third power of these tubes in bending and torsion, and they're able to actually produce a structure that maybe looks heavier, but it's actually lighter. We talked about the modes of loading, very important. Remember, tensile, stretch, tensile, compression, shear, and then bending and torsion and buckling. We talked about the stress distribution in a beam that's subject to those three modes of loading, and how things are very different for each one. For tensile, if you have these beams, the load scales with the height at the cross section linearly. In bending, the stress goes down with this dimension h to the cube power, and then in torsion, the stress goes down with the radius to the fourth power. So a very dramatic drop in stress. We try to put a graphic in place of what that looks like. I may not have succeeded, but you guys can go back and look at this. We talked about two tubes that are under pure bending. We discussed how you can actually make a tube that is just as stiff but much lighter by increasing the diameter and decreasing the wall thickness, taking advantage of that r to the cube or to the fourth power. And we talked about the constitutive laws of mass of lightweighting, of mass savings, as I call them here. And normally in normal semester, when I'm in class with the students, with you guys, I would go through the derivation of these, and I didn't do it last time, so I felt guilty. So I went ahead and put it together in this presentation here. Instead of writing it on the board, I'll just show you how this works. I'll try to go through this calculation. So not to show you guys I'm good at algebra, but just to show you that this is how these calculations work. And if you come up with some different type of loading or something, and you want to derive these equations on your own, you'll know how to do it. So I'll just go through this. The stress, so we're gonna take an example. We're gonna take the example of bending, okay? We're gonna take the example of design for strength. The stress in a beam in bending is given by this equation here, 12 times the moment times the distance from the neutral axis of bending, divided by the depth b, and then the height of the beam cubed. Okay, so you can then think of this being writing this equation for two different materials, or two different materials, sigma 1 and sigma 2, or material 1 and material 2, and then realizing that the stress is going to be highest at the maximum C value, so as far away from the neutral axis as possible, which is H, and that the thing is going to break when it hits the yield strength, sigma Y. And plugging those into the equation sigma 1 and sigma 2, you get sigma yield 1 equals 12m over BH squared. Okay, you can then, you draw that, you can write that equation for both beam 1 and beam 2, made of different materials. Then you use your wonderful algebra to put all the constants on one side. Okay, so you're holding the moment is constant, the B is constant, and 12 is obviously constant. So you can move all the constants to one side of the equation and all the variables to the other side of the equation, which gives you this equation here. So sigma y, the yield strength times the height squared equals 12m over b. And same thing here, same equation here, but with the second material or second beam. So the second yield stress material, the yield stress of the second material times the height of the second beam squared equals a constant. You can set these two together since it's the same constant. You can set them equal to one another, like you've done here. I've done right here, and then it becomes somehow relating H to mass, which is very easy to do. Okay, all you got to do is understand that mass equals volume times density, right? That's just the equation for density. Density equals mass by volume. So you can just rearrange this, and mass equals volume times density, and then you can start plugging in the dimensions of each of the two different beams, 1 and 2. So mass equals L times B times H times the density of that material from which the beam is made. You can write the two equations here, M1 and M2, rearrange those and solve for H. Okay, plug this H into this H up here. And this is just algebra, and you end up with solving this for sigma, rearranging this for M2 squared over M1 squared, and then taking the square root of both sides of the equation, and you get the familiar equation right here in the red box. So that is just this equation right here. Okay, pretty simple algebra, guys. You guys are MIT students. I'm sure this is like really easy stuff for you, but I just wanted to, I don't know what it is. Sometimes I sit down and I try to derive these equations and I can't do it. And I don't know why. Another day I'll sit down and try it again and it comes real easily. I think that there's just some order of operations here that you can get lost in if you're not careful. But if you solve the stresses in terms of H's and then plug in for the H's, it works every time. So just remember that. Anyway, you've now seen how to derive these equations. You guys can do this at home or in the library or your dorm room, and you can derive similar constitutive laws of mass savings. Clear? Make sense, guys? Okay. All right, see shaking heads. So we went then ahead and we took some table values for 6 different materials here. There's nothing special here. We just got these out of a book, like I told you never to do, but did it here anyway. We took these values and we went ahead and plugged those into these constitutive laws for mass savings. And we were able to rank the relative potential for mass savings as a function of these different materials. And you can go through here and look at the potential for mass savings given the use of all these different materials and these different modes of loading and design regimes. But what's interesting that comes out of this is that you don't always have to use expensive high-tech materials in order to save weight. You can actually save weight with steel compared to magnesium, aluminum, and titanium and fiberglass. So this really only happens when you have something that's under a tensile or compressive or shear load. But and you really can't beat carbon fiber because carbon fiber is just pretty amazing. But you can do better than aluminum and magnesium with steel if it's only in tension, compression, or shear. Okay, and that's if you're either in a design for strength or a design for stiffness scenario. And the reason this works is because steel has a very high stiffness to density ratio. Then the rest of this table, we go on to bending, and steel doesn't look so good. You really can't do as well with steel as you can with these other materials. If you're not taking into account, say, fatigue, for example. Aluminum has no fatigue limit. That means that there is some combination always of stress and cycles where an aluminum part is going to fail. As far as I know, magnesium has no fatigue limit either, although I have to probably look that up. I don't know for sure. Steel does have a fatigue limit, so there is an advantage there, and that's one of the reasons it works well in bicycle frames. Then I derive the rest of these equations for you. I also derive these equations for a tubular member rather than a solid member, and on and on. You guys can, I encourage you to go look through these tables and see the potential for mass savings that you can achieve depending on which material you use and what your mode of loading is and what your design regime is. And oh, I should mention this too. These calculations assume that you're using a steel that has a yield strength of 900 megapascals. That's actually a fairly strong steel. That's not your sort of garden variety steel that they make bridges and things out of. That's a much more high performance steel, something you would see in a bicycle frame, like a good chromoly steel. Okay, guys. I also have a Excel calculator that if you're really interested in, I can send you to try this on your own. These are Ashby diagrams. I believe this is where we left off at the last lecture. Oh boy, hold on one second. Stupid phone. Sorry. Okay. So these are Ashby diagrams. These are sort of bubble charts. I realized that in the last lecture, I actually had an error here. This was a Young's modulus versus strength graph and not Young's modulus versus density. So I have corrected that. And now this is the right graph, but this has bubbles that show the different Young's modulus to density ratios that you can come up with for all these different materials, for foams, for polymers, for wood, for ceramics, metals, composites, all these different materials. And they put these very convenient dashed lines on here. And what these are is these are lines for minimum weight design. And the strategy is to take a ruler and then plot out parallel lines, okay, to these dashed lines and see where they go through. And that will tell you which materials have the highest potential for giving you the stiffest design at the lowest weight, or alternately on the left here, strongest to weight. But they have these dashed lines have different slopes as a function of the different modes of loading, and that's what these equations here are. If you figure this out already, good for you. But these are really just the same things as this. These graphs are just a graphical representation of these tables here. They're exactly the same thing, except Michael Ashby did a much better job of it. But that's why he's a professor at Cambridge. Okay, now we're going to talk about, we've talked about bicycles, which is, I think, a pretty simple structure. And now we're going to ramp up a little bit more in complexity, and we're going to talk about body structures of cars. So here is a body structure for a early 2000s, mid 2000s Mercedes C-Class. I just happen to have this picture here because I pulled it out of a book I have. Okay, and this is out of a book that was published by Mercedes long ago. Long ago, Mercedes used to publish very highly detailed technical books on their cars that would have all kinds of crazy specifications. As far as I know, they only were printed in German. I'm sorry, they only printed in German. I have one of those books. It's in German. And anyway, they give these pictures of the body structure. There's some things that have been cut out here, like there's the cowl that usually is right here has been cut out. Part of the rear shelf has been cut out over here. Part of the rear floor pan has been cut out over where the gas tank would be. But this just shows you, I think, what the body structure looks like. So this structure that you're looking at, this is to a car. What the frame is that I showed you is to a bicycle. So this is the primary structure of this particular car. It's often called a body in white. Okay, so the body in white term comes from the state of these body structures when they come out of when they go into the paint booth. So they get a primer. The primer is white, and then they paint it whatever color you want the car, or they want the car. So that's why they call it a body in white, because the primer is white. So it's called a body in white, and you'll hear that term a lot in the automotive industry. So I have taken this, what looks like a pretty complex arrangement of stamped steel components, and I have broken it down into a series of tubes and beams, okay, that you can see in the lower right here, just to try to, I don't know, simplify what you're looking at here, to take a schematic, call it, of the different parts that make up a body structure. And here are those parts in a little bit bigger view so you can see them. I want to talk a little bit about as many of them as I can here without getting too boring. So going from front to back, let's say the front of the car has this bumper beam, and I'm doing this so you guys can sort of get some idea of what the different parts are, and maybe you start reading some Society of Automotive Engineers journal papers, or you read their automotive engineering magazine, and you from hearing these terms, you'll have a better understanding of what these different parts are, where they are, and most importantly for my purposes here is understanding how they're loaded, what the mode of loading is on each of these tubes, given different sort of global loading scenarios. And I'll get to what those are in a second. But so here's the bumper beam. Okay, the bumper beam is, can take a front impact stress, for example. That's what it's there for. And then it also adds stiffness to the structure too. It feeds load into these crush cans, which are special cans that are designed to absorb energy under front impact. Those connect into the front rail structures, as you can see here and here. Okay, the front rail structures are oftentimes one of the, I think, most highly engineered part of typical, garden variety car structures, because there's a lot that goes into getting enough stiffness out of them while also getting crush behavior out of them at an impact. Okay, what's attached to the front rails are these shock tower structures. I've only shown one here, but there's actually another one over here. The shock tower structures are actually one of the highest loaded parts of your body structure. And this is where you typically find fatigue failures in testing before the car gets launched to the public. I can tell you that I was involved with launching the Chrysler 300 and the Charger and the Magnum long ago. And during testing, we actually got cracks in this part. And we had to put on what's called a doubler, which is a secondary plate that goes, in this case, over the top to reduce the stress by adding more wall thickness. So this is the shock tower. There are structures behind the front rail here that feed the load further back into the chassis, the body structure. These are the rocker panels and the inner rails. There are typically, in a good, well-designed body structure, there are what are called torque boxes, which are structures that feed the load from these front rails into the rocker and into the inner rails. You can kind of sort of maybe visualize this in your head, that if you get into a front impact, the load first goes into this bumper beam. It transfers through the crush cones, which hopefully crush so nobody gets hurt. And then the load sort of flows down the front rails into the torque boxes and then back down into the rocker and into the inner rail. So you can kind of, maybe you can kind of visualize this in your head, that you've got these, this load that kind of goes back through the rails, and then it sort of bifurcates. Okay, the load gets fed into the rail on the rocker on one side and the inner rail on the other side. Okay, so that's how the auto manufacturers are able to dissipate so much load in an impact, in a front impact in this case, by feeding that, by distributing that load over as many structural members as possible. Okay. Then there's the rear rail, which typically has what's called a kick up in it. Okay, because they have to put the rear seat somewhere and create clearance for the rear suspension. It has typically its own set of torque boxes, and it goes back to the rear rails. Okay, here's the rear rail, which then bolts onto the rear bumper beam back here. And in a rear impact, you can also see how the load is similarly distributed as it would be in the front, except it feeds in from the back of the car and then distributes itself to the rocker panel, the rocker rail, and then in some cases, depending on how well the car's engineered, also to the rear rails. I'm sorry, the center rails. These guys here, the inner rails. Typically, it's easier to make a car meet front impact, or I'm sorry, it's easier to make a car meet rear impact than front impact. For most cars, I mean, obviously this isn't the case with like a rear engine car like a Porsche 911, but the idea is that you have, it's much easier, there's much more metal to crush in the back of the car typically than there's in the front of the car, because there's no engine in the back of the car most of the time, right? Some cars, but most cars out there, most gasoline powered cars take up that load very easily in the rear because they can crush and dissipate lots of energy in the front. It's a different story. I should probably mention at this point that this diagram is probably going to look very out of date in about 5 years from now, because electric cars change the scenario very dramatically. We'll discuss a little bit about that later, but that's probably something I should add in the next lecture. Everything I'm telling you right now changes. A lot of this changes dramatically when you get to an electric car and you don't have some big heavy engine, piece of cast aluminum sitting in the front of the car. We'll talk about more about that later. But just going back into this, there then is this structure that goes up and over from the front rails to the rear rails. Call this a roof rail, and that's this curved structure right here, right? And then there are what's called a B pillar. That's the structure right here that transfers the load in a side impact from the rail, from the rocker to the roof rail. And then cars have this, which is often made of high strength steel, is this roof bow, which transfers a side impact load from one side of the car to the other side of the car. And then there is the front and rear header, which do the same, but to a lesser extent. The roof bow, this piece right here, like I said, this is oftentimes made of very high strength material, because the difference is in a side impact. In a side impact, you're really trying to stop intrusion. You can't have any deformation because you're trying to keep another car out of the passenger compartment. Whereas with the front and rear bumper beams and the front and rear crash structures, you want to deform a lot of material. You want to absorb a lot of energy so that impulse loading doesn't go to the occupants of the car so they don't get injured, right? But the side impact, it's all about keeping people out, keeping other cars out of the inside of the car altogether. So it's all about stopping intrusion. So you don't actually want a lot of crush space. You want things as rigid and as hard as possible, as strong as possible, so another car gets inside the passenger compartment in the side impact. And this is a place where almost always you see a lot of martensitic steel. For example, B pillars. A lot of modern cars have martensitic B pillars, along with same with the roof rail. They're made out of martensitic steels. And this is a scenario where it's really preferable to not make these parts out of aluminum. Even if the rest of the car is aluminum, a lot of times these parts really are better off made in steel, because you don't have the packaging room, right? Because these are structures that would limit the amount of well, there's two reasons you want to use martensitic steel. One is that you want to make sure that these materials are as strong as possible to completely limit any intrusion. And also, because this is sort of the place where the passengers live, you need to have as little room for structure as possible, and as much room as possible for occupants, because that's a lot more comfortable, right? So these structures, really, you have limited packaging room, and you need as high strength as possible. So with aluminum, you can get the strength you need by taking up more packaging space. We showed that up here in in these equations. You can just go to a bigger, you can go to bigger geometry to up here. You can just go to something bigger in order to in aluminum in order to get the strength you need. But in these areas down here, you just don't have that packaging space, so you're very limited. So this is an application where really steel is typically the best solution. There is some carbon fiber out there. The BMW 8 Series, 7 Series. I believe the 7 Series has this roof rail made out of carbon fiber, even in high volume production. Anyway, you typically see things like steel side intrusion beams that are made out of martensitic steels. These roof rails and this B pillar also affect the rollover crush performance of the body structure as well. So this is a big deal in this country with, I guess it is in Europe too, rollover accidents. A rollover accident in a car or a truck is especially brutal. Sometimes the car can spin around at RPMs approaching like 100 RPMs per minute or faster, and occupants can get sucked right out through open windows if they're not wearing a seatbelt. But eventually the car lands, and it lands with the full weight of the vehicle on this roof rail. And so this has to be really strong in order to stop the roof from crushing down. And there's a lot of discussion here about what happens first. The occupant's head hits the roof, or the roof comes down and hits the occupant's head. And I don't really know, but there's a lot of people out there talking. The bottom line is that having a vehicle that doesn't deform in this roof crush mode is very critical. And so it's very important that these roof rail structures are made of high strength material. Volvo, I think, was one of the first companies, if not the first company, to make these out of boron martensitic steels. Strong stuff. I think they still do, and I think everybody sort of adopted that. So I've shown you pretty much I've shown you most of the longitudinal structural members in this body structure. Of course, there's also you have to have structure that's going cross-car, so transverse structures. So we've got the cowl member. This is right below the windshield. Toe board cross member. That's kind of in front of the brake pedal, but behind call it the firewall, the dash panel. There's cross members here and here. Seats are typically mounted to those structures, but they also provide side impact support. And then there's this rear cross member right here. This typically, in a lot of typical paradigm today, this has gas tank structure in it, for example, and this has to be strong in order to stop the gas tank from being compromised in an impact. And then a lot of times there's a rear cross member that goes kind of right in front of the tire tub where your spare tire might be, if you have a spare tire, which not all cars do today. And then there's this partial shelf cross member, and the loads from the shocks sometimes are taken up by these rear rail structures. I'm talking about the rear shocks and springs, but a lot of times there isn't a separate structure for those, and the load is just taken up by the rail here. The thing to think about here is that when you're talking about just driving your car on a normal day when you're not getting into an accident, which hopefully is 100% of days, the highest stress portions of the car is really the shock towers and where the load feeds in from the road from the suspension. Those are the areas that need to be most carefully designed so that there is no fatigue failures. There are no fatigue failures. When you're in an impact, which hopefully never happens, but of course we live in the real world and that does happen, the rail structures, and depending on the type of impact, the rail structures and these B pillars, these are the areas in a roof rail. These are the structures that need to be the strongest in order to take up the loads from those front or rear or side impacts. The jargon that's used in the auto industry, just so you know, is A pillar, B pillar, C pillar. Okay, the A pillar is this pillar right here. This is where you kind of, you look out when you're taking a right turn, you'll obviously look right at this, or a left turn, you'll look at this A pillar, but this is the A pillar. This one right here where the front seatbelt mounts is the B pillar, and then the one right back here that blocks your view when you're switching lanes on the freeway, that is the C pillar, okay? A, B, C. And then if you have, sometimes obviously with a big SUV or something like that, you've got more room back here, and instead of the roof sloping back, it goes straight back, and there's another pillar right here. Sometimes they call that fourth pillar the D pillar, like duck. Okay, that's just some jargon that the automotive industry uses. You can remember if you want. It might make things easier if you start reading automotive related journal papers. Okay, so I think that covers every structural member in the body structure. Any questions here on this? That makes sense, all these different little members?
Mm-hmm. You mentioned the 7 Series has carbon fiber roof rails. Was the motivation to turn those into carbon fiber over other members more of a safety consideration because they thought it could handle the loads that they expected on that better, or is it more of a moving the center of gravity down towards the road?
In regards to BMW, it's the second one.
Mm-hmm. So mostly a performance thing? Yeah,
it's so BMW, my experience with their body engineers is that they do, and I'm not saying like their other engineers don't think this way too. I'm saying I've only really had interactions with their body engineers. They do tend to be very focused on weight distribution, more so than other car companies. They want to have the center of gravity low, and they want to have their 50-50 weight distribution. Consequently, they will pay more money to put materials with higher strength to density or stiffness to density ratios higher up in the vehicle, or in the front of the vehicle, right? So that they can shift the big heavy engines up in the front. They want to shift the weight distribution rearward, right? So if you lighten up the front, that's one way to do it. So yeah, they'll use carbon fiber. I think it was the 7 Series. They use carbon fiber rails, and I think they also used a carbon fiber roof bow, and I think they also used a carbon fiber roof to try to reduce the weight of the greenhouse, they call it, and move the center of gravity of the vehicle down. It's and then they've also done a lot on the front of the vehicle too. They sort of pioneered this aluminum shock tower design. I don't know if you've seen that. I think it was one of the late 2000s or late 2000s. It was like one of the late 2000s. 5 Series was one of the first cars to use a cast aluminum shock tower. So this part right here got cast out of aluminum. That's also to reduce the weight of the front of the vehicle and shift the weight distribution rearwards. You know, as you get to these bigger and bigger engines, right? You put a V12 in there, it gets pretty hard to get 50-50 weight distribution, right? Because the engine weighs so much.
7 Series has a V12, doesn't it?
I think there's it's not the Alpina version, but I think there is like this, maybe it's the 755. I think there's one, or 760. It's the 760, that's right. The 760, I think, has a V12 engine, yeah.
Wow.
Another thing to think about too is like this car, like think about how much it weighs. These cars are like really, really heavy. I mean, they're like 4,000 or 5,000 pounds. And then if you I think their goal is to get like 3 to 5 times the strength out of the roof structure, 3 to 5 times the weight of the vehicle, so that so if the car is inverted, it can support 4 to 5 times the weight of the vehicle before there's any plastic deformation in the roof structure, right? So you have to have a lot of strength up there, and I guess I can sort of see how this in my head. I can kind of speculate like how this must have unfolded at BMW. It must have been like, well, this car weighs 5,000 pounds. If we're going to get, say, somewhere between 15,000 and 25,000 pounds capability of this thing when it's turned over, we're going to need a lot of heavy steel up there in order to support all that weight structure, all that heavy structure, right? So, okay, let's start putting, high strength martensitic steel up there. Well, gee, you need a really thick wall thickness. Now we got a problem because our CG's crept up. What do? Okay, how about carbon fiber? Well, over here in Regensburg, we have this huge operation that just spent the last 10 years developing mass volume carbon fiber. Let's just take advantage of that. So I can kind of see how that unfolded. In case stop me if I told you this, guys, already, but like BMW had this carbon fiber development program going on from like the late 90s to make high volume carbon fiber. So they probably poured billions of dollars into that program, and they weren't real shy about it. They didn't hide a lot of stuff. I remember, I think I told you this already. I think my boss one of my bosses at Mercedes actually would go there on a regular basis and talk to his buddies and like look at their carbon fiber production. So, or where their research was going. So they invited in a lot of suppliers, even competitors like Mercedes, which was shocking. And they developed this high volume carbon fiber, and that's what led to the BMW i3 and the i8 ultimately, and then also the carbon fiber roofs that you see on M3s and carbon fiber fins, strut tower braces, etc. So anyway, so they have that, they've invested that money. Now they got to justify it. Now they got to figure out where to use it, and this is like a really nice way to use it, was in those roof rails on the BMW 7 Series. Anything else, guys, on this? Okay, so now when you read Road and Track or Car and Driver or whatever blog on the internet, and they start talking about ABC pillars or cowls or roof rails or whatever, you'll know what they're talking about. This is so looking at some of the global loading conditions that I've already mentioned most of them here, but I'll just go through just again just to make sure. The global loading conditions that would be put on this body structure. These are the sort of the main loading conditions that are used to design the body structure. The front and rear impact are probably some of the most challenging. These are often simulated in CEAE or FEA, finite element analysis, before real cars are made, and they have different strategies. Car companies have different strategies that they use in order to best simulate a front or rear impact or side impact in finite element land virtually. And there's typically they'll hold these vehicles by the shock towers. That's what these little triangles are here for. And then they'll constrain the body from moving in different directions, 1, 2, or 3. So 3 is in the Z direction, and I think 1 is in the X direction, and that's this way. And then I think 2 is in the Y direction this way. But anyway, these vehicles are held, and then the then they're held by those shock towers, and then they're a lot of times you'll simulate this by putting a distributed load on the front bumper or the rear bumper or side of the B pillar. So those are three loading conditions that body and weight structures are designed for. Torsion and bending are two other very important loading conditions. Torsion is very critical for the way a car handles, the way it responds to steering inputs, to some extent the way it, well, also the amount of grip that the car will have, the ability of the vehicle to take advantage or to get as much out of the four tires that are on the road has a lot to do with torsion. Torsion is oftentimes simulated in FEA by holding the rear of the vehicle by the suspension mount locations like the shock towers, and then twisting by the front shock towers. So you apply a load in opposite directions on the front shock towers, so that you simulate the twist of the body structure that it would typically see in the real world when it goes into a corner, when it begins to turn in, when a car begins to turn in. Bending load is also something that's very important. Bending load has more to do with the comfort of the vehicle going down the road and less to do with handling. This is because when you hit a big bump in the road, you don't want the body structure to start getting to an oscillation, right? You want it to hit the bump and then stop, and then not flex back and forth a bunch of times. The stiffer the body structure is in bending, or the stiffer it is anywhere, I guess. The stiffer it is in bending, the less chance that you hit a bump, it's going to hit some frequency, right, and start jiggling around, and customers can feel that, or they can hear it sometimes too, and they don't like that, and then they'll rate a car as being loud or uncomfortable. This is simulated in finite element analysis by holding the shock towers in various directions, as represented by the triangles here, or holding the suspension mounting points in various directions. And then typically what they'll do is they'll apply a load in the middle of the driver's seat downwards, and that's how they typically measure bending stiffness. And this is across the center of the front seat because it well represents what a driver or a front seat passenger might feel in a bending event, hitting a bump. Okay, there are a couple other important global loading conditions that are simulated on body structures. Kind of for simplicity here, I didn't go through all of them. Another one that's kind of important to think about is the local stiffness at the suspension mounting points. There's a lot of work done to make sure that where the actual suspension control arms and springs and shocks and stuff like that, where they go into the body structure, that those areas are locally very stiff. Again, if you hit a bump, if those attachment areas are not stiff, then you can get into sort of these local vibration modes, which then get transferred to the drivers feeling loud or noisy or uncomfortable. So car companies pay a lot of attention to that too. There's other ones like curb push off. I guess that's one of the most, highest stress events, is that if you're parked at a curb and you're too close to the curb and you turn the steering wheel in the car, and the rear wheel, or the front wheel turns, and then the back part of the front wheel hits the curb and pushes the car out from the curb. That's a high, believe it or not, it's a very high stress loading condition. So cars are very carefully designed for that. We talked a little bit before about single shear versus double shear. A couple lectures, was it last lecture? So again, this is something that's very critical in suspension mounting. On a lot of high-end cars, they'll go through a lot of gymnastics to try to make sure that all the suspension loading points are in double shear. In some cars that are perhaps not so, I don't know, maybe the customers aren't that particular, or the company doesn't have the money to do things the best they can. A lot of times suspension mounting points are left in single shear, but this all goes into the structural efficiency of the mounting. If you want that mounting point to be as stiff and strong as possible, then you can get a stiffer, lighter structure by using double shear than you can single shear, but you are going to have to pay more money for it almost always. Okay, so the next thing we can do is we can go ahead and we can look at these 5 global loading modes, okay? Bending, torsion, front impact, rear impact, side impact, and then begin to look at what is the stress, or what is the mode of loading the mode of loading in the structural members that we drew in this schematic here. Okay, and the results from this table. So this table shows, like, for each of these different beam structures within the body structure, what type of loading are they typically, what mode of loading are they typically subject to? Bending, compression, shear, okay, or buckling, and torsion. The results of this table were calculated using finite element models when I was at Chrysler, and I think most of this was published in a paper that I published. I think it was in 2000 or 2001, and you can go ahead and look that up if you want. It describes this a little bit better, but this is a pretty complicated table. It's kind of a chart, an eye chart from the optometrist. Let's make it a little bigger. And you can go through this if you're interested, but it effectively says that these different beam structures that are in a car body, that are in a body in white, not all of them see bending loads. Some of them just see tensile loads. Okay, some only see bending loads, some see compression loads, but never see anything else. And it's because of this that the mixed material solution a lot of times can make a lot of sense in a car body. You don't need to use aluminum or carbon fiber, magnesium all the time in order to get the lightest structure, overall structure for the vehicle that can handle all your loading conditions. There's certain times that certain components that you can make out of steel and still end up with the lightest structure. There's other components that have to be made out of more advanced materials. Anyway, I'm not going to go through this table because it's pretty tedious, but you can go through and you can look at how these different things are loaded and consider how they're loaded given all the global loading conditions. Okay, and then you can begin to see which structures are more reasonable, are better made from steel, which ones are better made from aluminum, maybe which ones are better made from carbon fiber. And this is really getting to the most efficient design at the lowest cost. Steel is inexpensive, aluminum is expensive. Steel is inexpensive, aluminum is expensive. Magnesium is expensive. Magnesium is hard to corrosion protect, although they're getting better at it. And carbon fiber is hyper expensive. So you can see, well, if I can make this part out of steel and make this part out of aluminum and make this other part out of steel and this one aluminum and this one aluminum and this one magnesium, etc., then you can begin to see where you find the kind of optimum balance between mass and cost, right? Okay, cost is cost is obviously crazy important in the automotive industry. There's just so many players in the automotive industry that a lot of times they have to fight each other on cost. The Honda, Nissan, Chrysler, Kia. These companies really compete against one another on cost. But at the same time, they're under pressure by the governments of the world to reduce weight, right? So they're constantly looking to find these solutions where, where can I get away with using steel and reduce weight? Where do I really need to use aluminum so I can reduce weight, but I can just increase the cost by a tiny little bit? So a chart like this can come in very handy, I guess, for these companies that are trying to optimize their combination of costs and strength and stiffness and weight. Okay, so that is it for section 4. Any questions, guys? We've got a couple more minutes here, so we'll keep going, but any questions before I move on?
Can I ask you, what do the dashes mean? If it doesn't have compression, shear, bending, or torsion symbols, what does that mean?
It means that they're not very heavily loaded under that particular global loading scenario.
Okay, so I get it. So they'd all be, all right, got it. Some have
So in
some have
bending,
a little bit of everything. Some have only in one direction.
right. So take like a roof bow, the thing that goes between the B pillars that's good for side impact. In bending, longitudinal bending, there's really not much load there, very little actually. But in torsion, it begins to take a lot of load. In a front impact, I don't think it takes much load. In a side impact, it's obviously very critical. The roof bow transfers load creates that load path across the car that goes up and above your head instead of, through your chest, for example. Right, so very important. That one takes a lot of load inside impact, but not much under bending. So that's what the dashes mean.
Got it. Sorry, I was slow on the uptake.
No, that's fine. Like I said, questions are good. Active learning. Anything else, guys? Okay, section 5. We only have a couple minutes, but I will try to explain this. Okay, we might go over just a little bit. So back in September of last year was the Tesla battery day. And to my surprise, I watched this with great anticipation, was really excited to watch it. Elon Musk is one of my big heroes, and Tesla's amazing. Interestingly, I got interviewed for a position with Tesla in like 2000 and when was it, 2009 or 2010, and I thought there was no way this was going to work. After having worked at Chrysler and Mercedes, I knew how difficult it was to start a car company and the amount of capital you needed to buy really, really expensive manufacturing equipment. So I thought there's no way Tesla was going to make it. So I was totally wrong. I'm in awe of the fact that they actually made it. Anyway, they had Battery Day in 2020. It turned into, I think in my mind, in a lot of ways, it turned into Metallurgy Day instead of Battery Day. Elon Musk spoke a lot about casting. He spoke a lot about aluminum casting. If any of you guys watch it. Did any of you guys watch this, by the way? Any of you guys watch Battery Day? Woo, did you watch it? Okay. It was a lot of fun. But he talked a lot about casting. He talked about the aluminum that they use to make this rear rail and cross member structure back here that they're planning on using on I think it's the Model Y. They talked about aluminum that if they made this gigantic piece out of aluminum, they wouldn't be able to heat treat it, because if they heat treated it, it would get distorted, and then it wouldn't be able to fit in the body structure right, and they'd have all kinds of problems. So they needed to come up with an aluminum that was strong without being heat treated. And they used, just so you guys know, they used ICME methods in order to develop a new alloy that had sufficient strength without being heat treated. Charlie Kuhlman, who is head of all materials for both SpaceX and Tesla, is one of the founders of Questech. So Questech was that ICME firm started by Professor Olson, okay, that I mentioned in a previous lecture. So Charlie was a graduate student at Northwestern University in the material science department. He did a lot of research in designing steel alloys. And then later, after Questech got off the ground, he started working on designing aluminum alloys. Some of these aluminum alloys, like I think I mentioned previously, went into the Apple Watch. And then he took a lot of that expertise and put it into the rear, these big castings at Tesla. So this is all very impressive. And it's, like I said, I don't mean to criticize Elon Musk. I don't mean to criticize Tesla. I think it's amazing what they've done. But there's a slight mistake they made, which you can see in this picture here on the lower half. So see if you guys can figure out what this is. So this is the rear rail, okay? This is this structure right here. I'm showing you right on the schematic I showed you previously. This is this rear rail structure right here. And they've got sort of this waffle structure right here. This is a casting. Can you guys see let's see if you can figure out the slight miscalculation here, why this may not be the best design. I'll give you a minute to think about it. Think about this body structure being under torsional loading. Anyone want to take a guess? Nick, you take a guess.
Is it because of those kind of triangular cutouts, or the kind of V that runs through that honeycomb structure, that it'd be weaker in torsion? You're
getting warm. Think of global, think of bigger picture torsion, this whole body structure.
Okay, big picture torsion.
Anyone else want to take a guess, or I'll just show you?
Don, is this a cutout, or is this the whole structure?
This is
a cross section?
It's cast like that. The structure is cast with that waffle
so
pattern.
it's not closed.
It's not a closed section, no. You're getting warm. I think you're onto something there. So when this whole body structure is under torsion, okay, the highest stress would be on the outside face of this rear rail. Okay, so the geometry has not been optimized for torsional stiffness, and as a result, they probably had to put weight somewhere else in order to meet their torsional stiffness requirements. targets for this vehicle because there's no structural member, there's no structural panel here, there's nothing here to take the load in the highest stressed area. They've just cut out there. Okay, so look, every car company has to make compromises, and I'm not really criticizing Elon Musk or Tesla because, like I said, I think it's amazing what that team has done. They've changed the world. I mean, all the world governments are pointing all the car companies in the world at making electric cars now instead of gasoline powered cars. So Tesla knocked that loose, and I think the world owes them an incredible gratitude for having done that. Having said that, there is a design flaw here. That this is not going to be the most structurally efficient design, and I'm only showing you this and talking about it under the context of trying to help you think about torsion loads, bending loads, how do individual members of the body structure need to look like in order to be the most effective, the most efficiently handle those loading conditions. And this is an example where they obviously had to make a compromise for some other reason, probably just castability or something, I don't know. But they did make a compromise here in order to get that. And they did lose some structural efficiency by using a structure like this. You know, if you go back and you look at this Mercedes here, and this is a steel structure. Can you see it? No, I guess you can't quite see it. Anyway, the same panel on this car, the same rear rail structure is made with just a box section, and that outside, very outside panel portion of the part is a solid piece that would be much more efficient at taking that global torsion load. So maybe there's a better way to do this. I don't know. Maybe they didn't really think about this. I don't know. Maybe they knew they were making a compromise, but they had to do it in order to get the part. I don't know. But anyway, I just wanted to point this out to help you guys think critically about structures. And now, believe me, when you guys walk around and you see some airplane or some boat or some car or bicycle or tractor or whatever it might be, you're going to start thinking about this stuff like, gee, that's interesting. Maybe they really needed to close that panel out. Maybe that really wasn't the most efficient way to do that. And not everybody gets this right. That's okay. But just, that's the point of this course, is that you can begin to learn to think critically about these different type of loading conditions and how the stress is distributed through the part, given the mode of loading. And you can yourself start designing more structurally efficient structures. Anyway, with that, that's it for today. Anyone got any questions? I'm a little over. Any questions?
Don, if you have a few minutes to stay on, I actually want to ask a little bit more about another thing they mentioned in the battery day, because that's going to be my presentation for this class.
Okay.
I was going to talk about how they changed their battery to a structural battery pack, where you've probably seen this. Instead of having beams in the traditional sense and then have battery packs that fits into the structure, they're going to construct the battery pack entirely structural to form the chassis of the car, and then bolt the front and rear end onto the floor. I was just wondering, how does that compare with the traditional structure?
So I was crazy excited about that when he talked about it. I remember he talked about using the canisters of the batteries to as separators for the panels to make the floor pan. So you guys have probably heard of carbon fiber honeycomb. Have you heard that term before? For example, carbon fiber structural panels, honeycomb structural panels. So if you have a flat piece of metal, okay, that's under a bending load, okay, remember I showed you that equation, the 12 MC over BH cubed. So the H is the thickness of that sheet of material. Well, with most cars, the floor pan is just it's just a very wimpy little, sheet of metal. It may only be a millimeter or a millimeter and a half thick. And you consider that your H, that millimeter and a half. And all of a sudden you see it's really not very stiff and bending. Car companies go through all kinds of gyrations to try to make that stiffer, because if it's not stiff enough, it actually starts to make sound. It's by far, only semi-structural when you have that. Yeah. So what they started doing in racing cars and aerospace is you take that little thin sheet of metal and you separate them. Okay, you separate them in some cases with foam or honeycomb, so that now the H increases in that equation, right? stress equals a blah, blah, blah over h cubed.
Yeah.
Right? So as you separate those panels apart, the stress in the part goes down very rapidly. Low stress means low strain, which means a stiffer panel at the same
Yeah.
stress level, right? So they do it in a very, very efficient way because, you know, the honeycomb or a foam, that the weight per
Lighter.
whatever, cubic whatever, that foam or honeycomb is very low. So you can get incredibly efficient structures by using honeycomb or foam to do that, right? And they do that very effectively on racing cars and airplanes. Corvette uses it. The General Motors uses it on the floorboards of the Corvette. But with an electric car, you've got these, you know, all these whatever thousands, I think it's thousands, maybe hundreds
Yeah.
of little battery cells, right? They're in these little steel cups.
Mm-hmm.
Okay, and you have that structure there anyway. Why not use it for two different things? One to hold the jelly roll of lithium, you know, alloy and graphite, you know, anode and cathode, and then also use it to separate the panels, the structural panels of the bottom of the car. So effectively,
Yeah.
what you're doing is you're just making a honeycomb sandwich, but you're using the battery structure twice, right? You're using the can twice. One, like I said, to house the jelly roll, and the other to separate the floorboards. Okay, so this has been done without, I mean, like for example, the smart car and the original A-Class Mercedes, they also used a double floor pan to increase that H value. But now with Tesla, you know, with an electric car, you've got the battery structure anyway, those little cans, use them twice to lighten up the vehicle, have them take two different loading scenarios. And that's what's so amazing and beautiful about the concept. And it's probably, I think what Musk was saying is that it's probably so effective that now you don't have to have as much structure. You can go ahead and bolt the rear sort of cradle or suspension or rail structure and front rail structure and cradle directly to the battery housing.
Yeah.
Okay, and use that battery housing as the primary structure of the vehicle.
Yeah.
Okay, and therefore you're getting two different functions out of that material, which means you're getting more loading per given weight. So that's what's so extraordinary about that idea. Later on in this lecture series, I'm going to show you a BMW motorcycle, or actually it's a scooter, where they did the exact same thing. Okay, probably would take a while to forward to it now, but anyway, I promise I'll show you. But they did BMW did the exact same thing with this scooter, and it's really cool. And it's so exciting to see that Tesla's going to do the same thing with a full car. So I'm excited about this.
Would you be worried about torsion? Because essentially you have two sheets, and if there's no strengthening mechanism crossing both directions, actually, it might be weaker in torsion than the traditional structure.
Well, if you think of the neutral axis of torsion going through, say, the center of the driver's seat, imagine a line in the middle of the car, you know, as high as maybe wherever the center of gravity or the polar moment, the center of the polar moment is, you know, wherever that is. I don't know, just roughly, let's say it's about halfway up the seat structure on the car, in the middle of the car, you know, crosswise in the middle of the car. You imagine that's the axis of torsion, right? And then you can begin to see that battery structure is under shear, right? When the whole car, the global loading on the body structure is under torsion, that battery box is under shear.
Yeah.
So if you can provide some of that shear holding capability with the little battery cans, then you should see an advantage.
Okay.
But the bigger advantage certainly will be in bending, global bending, global torsion.
Yeah, I agree. The bending should be very good.
Right.
Yeah.
And that's, you know, to be honest, like most customers will notice that long before they notice torsional stiffness. You know, torsional stiffness is more for sort of the fringe lunatic car enthusiast who goes around quarters fast. Or maybe even tracks their car. It's not so much about driving down the road and hitting bumps and things. Most customers notice a car is quiet and comfortable, has good so-called noise vibration harshness, NVH, when it has a high bending stiffness.
That's a good point. Yeah.
Anyway,
cool.
Good question. Really excited to see if they're able to do that. But what they're coming out with the Model 4, something which will be a less expensive, hatchback or something, a hot hatch maybe. So I'm looking forward to seeing that, and hopefully we'll be able to use that technique.
Thank you,
You're
professors.
welcome. Thanks for coming. All right, I
Bye.
guess it's time to sign out. Have a good one. I'll see you next week.
See ya.
Bye.